Transformer differential function testing, vector correction, zero sequence filtering. In this video, we are going to see differential functions and vector correction, zero sequence filtering of transformer protection. We are doing that explain about the testing of a differential function of transformer protection relay. In numerical relay, vector correction and zero sequence filtering are explained. You see the diagram. One transformer is connected to a balanced resistive load. Transformer primary current and secondary current is shown in the diagram. In the left side winding, A1, B1, C1 are connected to source. A2, B2 are connected to neutral. This is called star connection. In the right side winding, small letter A1 connected to B2, B1 connected to C2, C1 connected to A2. This is called delta connection. Now we say star delta connection or YD connection. R phase current, capital IR current, enters into capital A1 and comes out A2. In the delta side, R phase current, small IR, flows from A2 to A1. In the same way, Y phase current and B phase current also. In delta side, I1 comes from A1. So, load current from A1 is IR minus IY. IB comes from B1. So, load current B1 is IY minus IB. IR comes from C1. So, load current from C1 is IB minus IR. Star side, delta side current vector is shown here. Delta side current is leading by 30 degree with respect to star side current. We call this as 11 o'clock. So we call this YD11. Now we are going to see differential protection for this transformer. Here star side CT, secondary is connected as delta. Delta side CT, secondary is connected as star. Output from CT secondary are connected to differential protection relay. Before I explain this diagram, we will see under the testing of the relay. Biased differential relay. In this figure, 11, 15, 7, 14, 18, 10, 8, 16, 12 are current terminals of the relay. B is bias coil or restraining coil. D is differential coil. For R phase, terminal numbers 11, 14, 12 are used. For Y phase, terminal numbers 15, 18, 16 are used. For B phase, terminal numbers 7, 10, 8 are used. R phase current input is in terminal number 11 and output is in terminal number 14. This current is passing through bias coil. Differential current of IS is coming out from terminal number 12. Differential current is passing through differential coil. In the same way, Y phase, B phase current terminals are used. Setting of the relay. Rated current ION equal to 1 ampere. Differential current setting ID is 0.15 ampere. It is nothing but 15% of rated current. Bias setting is 45%. In this relay, available settings are 15%, 30%, 45% of bias setting. Figures shows the connection diagram of connection to test bias differential relay. Now we are going to test in R phase. One variac is connected to one ammeter to measure I1. input current. This ammeter is connected to the relay current input terminal through SPST switch, single pole single throw switch. Current output terminal of the relay is connected to an ammeter to measure I2 and a rheostat to adjust the output current. Differential current terminal of the relay is connected to an ammeter to measure ID and a rheostat to adjust differential current. Keep the variac at minimum, rheostat at maximum value. By adjusting variac and I2 variac, set I2 current at 1 ampere. By varying ID rheostat, increase ID current till relay operates. Note I1, I2, ID. Same test repeated for I2 to 2 ampere. From this value, calculate percentage bias. Same test can be repeated for Y phase and B phase. That is, we are measuring differential current at various bias setting at in R phase, Y phase, B phase. First, we measured operating value, that is differential current, for bias current equal to 1. Next, we measure the differential current for bias current is equal to differential current only testing. You remove the connection between I2 ammeter and relay terminal. Vary the rheostat or variable till relay operates. It is approximately 0.15 ampere plus or minus 10%. And note it. Repeat for Y phase, B phase and note the operating value for differential setting of 0.15 ampere. Switch. Now you see the table is given here. You enter the values and find the accuracy of bias setting. Bias slope is shown in the top of the table. X-axis is bias current. Y-axis is differential current. If bias current is more, relay operates at more differential current. If bias current is less, relay operates at less differential current. Assume relay bias setting equal to 45%. If bias current is 1 ampere, then operating current is 0.45 ampere. Relay continuously operate if the operating current is more than 0.4 ampere. If bias current is 2 ampere, operating current is 0.9 ampere. Relay continuously operate if the operating current is more than 0.9 ampere. That is, initially setting is in ID, that is 0.15 ampere. Due to bias current, the setting is increased to some other value. What value? The setting is 0.15 is increased to some other value means due to bias current only it is increasing. That is it. Now differential current setting is equal to bias current into bias setting by 100. The slope is called bias current slope. If you know the bias current, you calculate the recorded differential current from formula or graph. Now we will see current flow to relay from CT second phase. Star side CTs are connected in delta and relay is connected. Delta side CTs are connected to relay. CT primary current flows from P1 to P2. Secondary current flows from S2 to S1 internally. So externally, current comes out from S1 and going to S2 through connected cycles. From star side CTs, IY minus IR, IB minus IY, IR minus IB are going to relay. From delta side CTs, IR minus IY, IY minus IB IB minus IR are going to relay. The current, both the currents, that is input current and output current, are summed together and coming via the difference relay. Now, both the currents in R phase, input and output current, summed, the difference current is equal to 0. In other words, IR minus IY minus IB minus IR are going into relay and coming out from relay. You see in this diagram, IR is going, IR minus IY minus IB minus IR is going one side and coming out from our other side. Secondary current circulate via bias coil of the relay. No current in differential coil. So relay will not operate for this condition. Internal fault. You see in this figure, an internal fault is happened inside the transformer. That is B phase star winding internal fault was happened. During that time, the fault current is feeding from B phase earth and return to the source. In that time, the secondary current from the CT secondary is flowing into the relay and circulate among the differential coil. So the relay will operate immediately. External fault. You see in this figure. In this, an external fault is occurred externally, that is weight B fault after the CT secondary of delta side. The current flows from Y phase to B phase and circulate in the primary system. But in the same way, the current is from CT secondary, it will go to the relay and the relay current circulate among them. Fault secondary current flows in bias coil, relay not operates. Due to bias characteristic, relay needs more difference current to operate. Remote earth fault, zero sequence current circulation. Suppose any earth fault comes in the remote side, some other places, the fault current will circulate to the source through the easiest path. Some current will come to our transformer, star winding neutral, and go into the source. The fault current, that some fault current is coming via neutral and going to the source in the each phase windings. That is, suppose the fault current is some IF, one third of the current flows in R phase, Y phase, B phase. So totally IF current will flow to the system, that is source. Remote earth fault current flows to source through energized unloaded transformer winding. IF by 3 0 sequence current flows in ROIB winding. Secondary current circulates in CT secondary winding. No current in differential coil. Relay will not operate in that conditions. Suppose this star side CT is connected as a star, the circulating current will come to the CT secondary and go to the relay. Now, CT secondary of the star side winding is connected as a delta. So, the remote earth fault current which is entering into the star winding, that will be circulating in the CT secondary of the star winding. Now we are going to analyze transformer protection with the given data of transformer. Transformer data are 50 MVA, 230 kV bar 115 kV. That is star side face to face voltage is 230 kV. Delta side is 115 kV face to face voltage. Configurations YD11. Percentage impedance is equal to 12%. Now we will calculate what is the full load current. Full load current, that is transformer side, star side, primary is 125.5 ampere. Full load current delta side, primary current is 250 ampere. We are using CT ratio in 230 kV side, that is star side is 125 bar 0.577. In delta side, CTR equal to 250 bar 1. So full load current secondary, that is inside of the CT in star side, that is delta formation, 0.579. Full load current secondary in delta side is 1 ampere. So CT is secondary current coming out, CT current from CT secondary is in 230 kV is 1 ampere, that is 0.79 into root 3. In delta side CT secondary current is 1 ampere. This current 1 ampere circulate among the relay coil. Full load current or amplitude matched to flow rated current of the relay. That is, if the full load current flows in the transformer, rated current flow into the relay. Current vector are matched. That is, YD11 of the transformer. Now the CT secondary delta and the star connected. The current vector are matched. No zero sequence current. That is, in delta star side, CTs are connected as delta. The zero sequence current will not flow to the relay. Suppose CT ratio are different. You won't get the, if you are not getting the rated current to the relay, if full load current flow in the transformer, that time ICTs are used. ICTs are used for different CTs. Suppose the error of CT is 10%, plus or minus 10%. Assume the condition. In star side CT is minus 10%. Delta side CT is plus 10%. So totally you get 20%. That is, for 1 ampere, 20% of the current will flow into the differential coil at the time of full load current. If the relay is setting is 0.15 ampere, the relay may mal operate. That is why bias characteristic introduced in the relay. That is, if the bias current is more, you need more differential current to operate the relay. ICTs are used to maintain relay rated current to flow into relay under full loaded condition. That is called amplitude matching. Actually, relay setting is 50% of relay rated current. If we compare to primary system, setting ID is 15% of primary full load current. We can say 0.15 pu with respect to full load current. Delta connector ICTs are used to maintain current vector correction. Delta connected ICTs are used to circulate zero sequence current among themselves and no zero sequence current to the relay. Numerical differential relay. The relay is given for a protection to protect a transformer. Transformer data are 50 MA, 230 kV bar 115 kV, YD11. You see, in numeric relay, we have to feed the transformer data to the relay, in the relay. That is, star winding we are calling as A winding. Delta winding we are calling as a B winding. The rating of the transformer is 50 MVA. So, first we feed the rating of the transformer, then A winding details. Voltage is equal to 230 kV. CT ratio 250 bar 1. Then B winding. Voltage is 115 kV. CT ratio 250 bar 1. A to B, that is winding configuration. YD11. CT secondary of A winding and B winding are connected to the relay. There is no delta connections or ICTs in this circuit. What is, once you charge the feeder transformer and loaded, the load current flow into the transformer. The secondary current will come to the relay. That what the relay is doing, first you consider the A winding current. The A winding current zero sequence filtering is happening in the relay. What is zero sequence filtering? Summation of all current divided by 3 is subtracted from each phase current of A winding. This is called zero sequence filtering. After zero sequence filtering, it is due to vector correction. That is, first A winding is a reference winding, so no vector correction, it is considered as a zero. Then amplitude matching. The current is zero point 0.5 ampere is coming to the relay. That is under full loaded conditions, zero point 0.5 ampere is coming to the relay. So you have to feed 1 ampere to the circuit measuring program. So multiply by this 2, you will get that 1 ampere. This is called amplitude matching. Delta side CT is connected to the relay. First, the zero sequence filtering is happening as in the star side current. That is summation of all current divided by 3, and each phase current is subtracted by this current. Afterwards, that is given to the vector correction. Here, the delta side CT is 30-degree leading current is coming to the relay. So first, the delta side current is shifted to 30-degree lagging and in phase with the star side current. That is called a vector correction. Then amplitude matching. Here CT ratio matched with that one. So 1 ampere is coming. 1 ampere directly it is given to the measuring unit. Now the measuring unit or measuring program compare both the things, and it depends upon the condition. If the differential current is more than set value, immediately it will give a tripping command. All currents are converted to PU with respect to its full load current and used for operation and or restraining. Thank you very much for watching this video.